Hopefully you've had a chance to try these practice problems for the lecture. I'm going to walk through the solutions now one at a time. And I'm going to start with this one about a xenon chloride laser used to body scan the Turin shroud. So the laser uses a wavelength of 308 nanometers and a pulse of energy of 50 milliwatts. And the question is, how many photons were emitted in that one pulse? So right away, this how many photons and part of the question is telling me that it'd be helpful to know the energy of one of the photons because I compare that with the total energy in one pulse and I can figure out how many of those photons had to make up the pulse to get to that total energy. So the information I have is a wavelength of 308 nanometers. I have an energy equal to 50 milliwatts. And that's basically what I have. So what we're going to do is figure out the energy of a photon and then figure out our total energy. Sorry, that watts became a W when I didn't finish it. So that energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. So with just that wavelength piece of information, we have enough to calculate the energy of the photon. That's really all we need. Either the frequency or the wavelength can get us to the energy of the photon. So this is going to be equal to that 6.626 times 10 to the negative 34th joules seconds. That is my Planck's constant. Now times the speed of light, which is also a constant, 3.00 times 10 to the 8th meters per second. All right, so already my seconds cancel out. I have units of joules and meters. And now I'm dividing it by my wavelength, which I have units of nanometers, and I really need that to be in terms of meters. So that way it cancels out the meters in my speed of light constant. And then I'm left with just units of joules. And then that's a reasonable unit to have for just the energy of a photon. So I'm going to incorporate that conversion into my equation here. So I have my 308 nanometers for my wavelength. I'm going to multiply that by 1 meter divided by 10 to the 9th nanometers. And so this is just that convection conversion that 1 meter equals 10 to the 9th nanometers that I'm using and landing on those dimensional analysis skills. All right, I've got a thing. I can plug it into my calculator. And when I do, the energy of that photon is equal to 6.45 times 10 to the negative 19th joules. Okay, so that's one photon, but I've got a lot of photons and I want to know exactly how many of them. So I am going to need to find out how much is in that pulse of energy. So we're going to make a little assumption that I probably should have put in the problem before you tried it, that this is a 1 second pulse. And so that means if we assume a 1 second pulse, we can convert the energy of that pulse into just energy in terms of joules. So we can go from that milliwatts to just joules. So if we are assuming a 1 second pulse, that means that we're going to have 50 milliwatts in that 1 second. So let's convert our 50 milliwatts. Let's get a little bit more space. Into watts. So 1 watt is equal to 1,000 milliwatts. And now we're going to convert into joules. I want 1 joule, and a joule is equal to 1 watt per second. So we'll go 1 joule. And since we're working with just a 1 second pulse as our assumption, we can make this kind of a quick conversion in that sense. And so we're going to convert this into 0.050 joules of total energy. So with this assumption, we can say that we really are looking at 50 milliwatts per second. And we're going to use a conversion factor. You can look up that a joule can also be defined as 1 watt per second. So if we take this 50 milliwatts per second, and we need to convert first using the metric system into just watts. So 1 watt is equal to 1,000 milliwatts. Now we have units that are watts per second, and we can convert that into joules of 1 joule is equal to 1 watt per second. So my units are going to cancel for the watts per second and leave me in units of joules, which is going to give me a total value of 0.050 joules. So I have a total energy now, and I have an energy of a photon. So to determine the total number of my photons, I just need to divide my total energy by the energy of that one photon. So let's create a little more space for this here at the bottom. So the number of photons will be equal to that 0.050 joules divided by the energy of just one of the photons, which is going to give me then a value of 7.75 times 10 to the 16th photons. So in that 1 second pulse, I'm going to have a lot of photons, about 7 times 10 to the 16th. Moving on to our next problem, we want to determine which of these colors of light would be able to eject an electron from a metal foil. And we find out that a photon with an energy of 3.976 times 10 to the negative 19th joules will match the binding energy of the metal that we have. And so which of these types of light can actually do that job? And so we have the energy of our photon is equal to that 3.976 times 10 to the negative 19th joules. And we really want to know what is that wavelength that it will correspond to, so we can make some calls about these colors of light. So the equation that I'm going to go ahead and use then is that energy of a photon is equal to the speed of light times Planck's constant divided by the wavelength. And I'm going to be solving for the wavelength right here. So plugging in my values that I have, I know that energy of the photon is at 3.976 times 10 to the negative 19 joules, which is equal to my speed of light, 3.00 times 10 to the 8th meters per second. Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. All right, all divided by my wavelength. So I'll solve for that by plugging this into my calculator and rearranging. And I get a wavelength equal to 4.999 times 10 to the negative 4th meters. So for comparison's sake, I'm looking at units of meters, and all of my wavelengths of light have nanometers. So I'm going to convert using the metric system where 1 meter equals 10 to the 9th nanometers to figure out what this corresponds to in terms of nanometers. So I'm going to take this value and multiply it by 10 to the 9th nanometers and divide that by 1 meter. And will give me a value equal to 500 nanometers if I round up to 3 sig figs. Oh, we're going to be at 4. So it'll be 499.9 nanometers, or basically 500. Okay, so that is the wavelength that will eject an electron. So this is that threshold value. So which types of light are going to actually be able to eject it? So this one has enough energy. So we need wavelengths that have an energy greater than that of a wavelength at 500 nanometers. So it's important to remember that as your wavelength decreases, your frequency increases. And as your frequency increases, your energy increases. So we are looking for anything with a wavelength less than 500 nanometers will eject an electron. So looking at our choices, that means that that violet light will do it, and so will blue light, but not green, orange, or red.